Swayam Prabha. Digital India. Educated India.
Okay, so good morning. In yesterday's class we looked at the method of separation of variables, which is an important technique for analytically solving partial differential equations. The idea is to split the PD into two ODEs, introducing a constant called lambda square, and the inherent assumption is solving the ODE is much easier compared to solving the PD. Okay, then we got the solution, general solution, then we had these boundary conditions. Using the boundary conditions we got we evaluated the constants A, B, C, D. When we are trying to evaluate the constants, several new things entered the picture, like there is a lambda and the solution is satisfied and lambda is equal to 1 pi by L, 2 pi by L and so on. So these lambdas are called eigenvalues of the problem, and then finally you got a solution in terms of sin n pi x by L and sin h n pi y by L. The sin h n pi in yesterday's class was basically because the temperature was exponentially decaying in the y direction. As far as the sin n pi x by L is concerned, it is basically repeating or a periodic boundary condition. In fact, it is because of this sin n pi x by L that you are able to use this invoke the orthogonality property. That is why this periodic boundary condition, the 0 boundary condition, is very important. Towards the end of the class we also saw that if you have a problem where more than one boundary condition is 0, then you have to use the superposition principle. Have 1 0 0 plus 0 0 1 0 0, you split the problem into several sub problems and use the method of separation of variables to individually find the solution and then get a composite solution, which is the additive sum of all these solutions. Okay, but now you can see that even for a 2-dimensional problem, 2-dimensional steady state, steady conduction in a slab with constant properties, getting the analytical solution was quite involved, and then finally you have to evaluate a series. It is not that you got an expression like e to the power of minus mx or e to the power of, so you have to evaluate a series, and then the accuracy of your solution depends on the number of terms you retain in the series. So it is not very convenient, though we claim that it is an analytical solution and so on. You will soon realize that if you evaluate the heat flux using this series, you require many terms. It is not so easy to get the heat flux with, because again the temperature has to be differentiated, and then the k dt by Tx term will contain so many terms in the series. So and for certain other types of boundary conditions, for example, you have Q, which is a function of x, and then you have a convective boundary condition on one side, you have two other temperatures on the other two sides and so on, then it becomes extremely formidable to solve these problems. And the moment you say thermal conductivity is not a constant and so on, it is very difficult to solve these problems. Therefore numerical techniques were developed, and the growth of the numerical techniques was also accelerated by the development of computers, okay, and then the availability of programming languages like Fortran and so on, which enabled engineers to tackle these problems. Of course nowadays you have got suites like MATLAB, which can solve many of these problems, and you have got libraries which solve ODEs and PDEs in Fortran and all that. And there are commercial software like COMSOL, which is very powerful, based on finite element, and Fluent, which is based on finite volume, which can solve all these problems with considerable ease, right. So the engine behind all this software is some numerical technique. So these numerical techniques, broadly the numerical techniques which are used in conduction, in heat transfer, basically are either the finite difference method, As far as heat transfer and fluid flow are concerned. The first two are very popular, the third is not so popular, but still there are some practitioners who would like to use the finite element method for both fluid flow and heat transfer. Finite volume, most of the commercial software, our Fluent works on the finite volume method. So essentially what is the basic difference between finite difference, finite volume and finite element method? The finite difference is different from the other two because the finite difference method is based on the Taylor series approximation of a function from that you get the first derivative, second derivative, and then you find out what is the value of the nodal value of temperature or velocity or whatever variable under question as a function of its neighboring nodes. And then once you set up a system, finally you set up a system of linear equations which is solved by matrix inversion or Gauss-Seidel, Gauss-Jacobi iteration and proceed. That is how a finite difference work. A finite volume method is basically a control volume technique. It is also called the control volume method, where you take a control volume and find out what are the fluxes which are entering, what are the fluxes which are leaving, any other heat generation within the medium or any heat storage or heat depletion, that is enthalpy increase or enthalpy decrease in the medium. Okay. So it is basically like a you are looking at the law of conservation of energy as far as conduction problem is concerned and writing down all the terms and finding out an expression for the value of the temperature at a particular node. Okay. So there is no Taylor series expansion in a finite volume method, and in a the finite difference method we finally evaluate the derivative at a point. But what is this point? We have to be very careful. Does the point have area and volume? Okay. If the point does not have any area and any volume, then you cannot define stress and something, for example stress cannot be defined at a point and so on. So finally we have to have that in mind. Okay. In the limit delta x delta y tending to 0, that means delta x cannot become 0, then you are in trouble. Okay. So finite volume method is quite natural because it is based on finite control volumes. You do not reduce it to infinitesimally small size and make it a point. So naturally the finite volume method can handle certain types of things. So the finite element method is actually a cousin of the finite volume method, where also the governing equation is integrated once. When the governing equation is integrated once, conditions like the Neumann condition like dt by dx is a constant, or for example dt by dx equal to 0 is very frequently encountered in conduction problems. If you have n surfaces in a problem, one or two of the surfaces may be insulated. dt by dx is equal to 0 is very easily handled by a finite element method, because the governing equation is integrated once, and then you start finding out the equations for a particular element, then you find out the equations for all the elements, assemble all these elements, you get a system of linear equations. Beyond a certain stage it becomes again like a finite volume method. Okay. So you integrate the governing equation once, but in finite difference method what you do is you take the governing equation, start discretizing I plus 1j I minus 1j. We do not do that in a finite element method, but anyway that I minus 1j ij everything will come in the end. Instead of using the ij notation in finite volume and finite volume method particularly, we will use east west north south. Okay. Here we will use I minus 1j I plus 1j ij plus 1 ij minus 1. Okay. Now in these lectures we will look at the basic principles underlying the finite difference as well as the finite volume method. The finite element method is beyond the scope of this course. Okay. So finite difference. What is the basis? The basis is the Taylor series expansion. So the basis is the Taylor series expansion. Now let T be, let us say that you want to evaluate T at xi plus T is the temperature. I am, instead of using y I want to use T because T is frequently used in conduction. X is the spatial coordinate, so T is a function of x, it could be a function of x, y, z, whatever. Now for simplicity we say T is a function of xi. Using Taylor series we want to expand it as T is a function of xi plus dt by dx at xi into delta xi plus plus higher order terms. The higher order terms will become negligibly small when delta xi is properly chosen, because it is going to be raised to the higher powers of delta x. So if delta x is 0.01, this will be 0.01, this will be 0.01 squared, this will be 0.01 cube, and remember at the bottom also is 2 factorial, 3 factorial, everything is increasing. So higher order terms can be neglected, even though d squared t by dx squared may be significant and higher order derivatives may be significant. Okay. Now this equation can be rearranged for dt by dx. So rearranging equation 1, so this delta xi is small compared to xi, small expansion, that is very important. It is xi plus epsilon. If x is 100, delta x should not be 75. If x is 100, delta x can be 1, 0.5, 0.1 like that. It is called a small expansion. Alright, rearranging equation 1, you have plus so the key point here is you are anyway neglecting the higher order terms. If you say that dt by dx is equal to approximately this, then this will be the order of the error associated with the truncation. So the order of the error is directly proportional to delta xi. Since it is proportional to delta xi to the power of 1, it is called a first order accurate scheme. Okay. Therefore now if you write like this, now I say dt by dx okay is not 0, it is order of. That is a leading order. Do not ask me, sir, what about other terms are there, but other terms are much smaller compared to this fellow. So the maximum culprit, maximum error will be caused by delta x. The next term is delta x square by 2 factorial, and anyway delta x itself is small. So this is the gives you the order of accuracy. Okay, this is called the forward difference. It is first order accurate because delta xi. Please be careful. We are neglecting only up to the second order. We are taking up to second order. Okay, we are taking up to second order, but when you get the dt by dx, we are dividing by delta x. Therefore, d square t by dx square gets multiplied by 2 factorial, right? It gets, so 1 delta xi gets cancelled. Are you getting the point? So it is first order accurate. So if you want to use this first order accurate scheme for solving your problem, you have to use more number of grids, because there will be a severe what is called this error is called the truncation error of the numerical scheme. Now this is for one node. In a problem, in a 2-dimensional problem, you may have dou t by dou x, dou t by dou y, d square t by dx dy, dou square t by dou y squared. Then each of this dt by dx is represented as a finite difference. Instead of a differential, you are representing it a finite difference. When you assemble all these, you will get a set of simultaneous equations for t of ij. I can vary from 1 to 20, j can vary from 1 to 20 depending on your grid. Then when you are doing these operations, the computer can store only a finite number of digits. repeatedly when you are doing Gauss-Seidel method, then there will be a loss, of information because the computer will truncate after a certain number of decimals, that is called round off error. Okay. So, the round off error will increase, if you are using more number of grids. When you are using more number of grids, delta xi will come down, therefore the truncation error will decrease. So, there is an optimum grid size at which the sum of these two errors, which is the total error, will be a minimum. So, if you plot the error, what are these two? Yeah, grid size is size of the grid, delta x increases. Because number of computer operations are reduced, because only you are solving on a 5 by 5, okay. You are solving on a 50 by 50, truncation error increases. What happened? Yeah, tell me. This is grid size. It is not number of grids. Grid size is the size of delta x. If the size of delta x increases, truncation error will increase, there is no doubt about it. I am not saying number of grid points here, it is 1 by number of grid points, it is inversely proportional to the number of grid points. Okay. You can plot the same thing as number of grid points, then you have to make it ulta, round off and truncation. Okay. So, this is about forward difference. It is also possible to use a backward difference. Now, what will be the backward difference? T of next term into minus and plus will alternate, plus this, what is this now? Okay, this should be 3 rearranging plus okay. So I can just write it as the backward difference is also first order accurate. This is called backward difference. Please note, we are trying to get expressions for dt by dx, dt by dy and so on, because we are frequently encountering partial differential equations. So we want expressions for dou t by dou x, dou t by dou y. More importantly, we want expressions for dou square t by dou x square and dou square t by dou y square, because only the mixed derivative, first derivative, second derivative, first derivative in time, second derivative in space, with that all combinations will be there, unsteady heat conduction, steady state heat conduction, everything will be covered. Of course, I am deriving all these only for the Cartesian coordinates, it will be little more involved, but using the same procedure you can derive the finite difference form approximations for the first derivative for both the cylindrical as well as the spherical coordinates. Now approximation of the second derivative, that is very important, because if you want to solve the Laplace equation, the d square t by dx square and d square t by dy square make an appearance, okay. So now we will have to look at the approximation of the second derivative. So please remember that even the backward difference is also first order accurate. Okay, approximation now T of can I write like this itself, or T of I plus 1, can I write it as I plus 1 or x of, we will keep it as x of I plus 1, okay, is equal to this is 6. This is based on forward differences, okay. T of So I am writing the Taylor series expansion for t of xi plus 1, okay, and I am also writing the Taylor series expansion of t of xi minus 1. No, in fact, now there are several ways of doing what if you want to do first. Instead of taking the second derivative, what I want to do first is, with the same thing several things can be done. We can call the title as central difference. Okay, before going to the, now subtracting 8 from 7. No, no, no. I want to find the first derivative. Okay, subtracting subtracting 8 from 7, we get txi get cancelled, 2 dt by dx, correct. Second derivative gone, third derivative is there, okay, plus now therefore minus minus so therefore dt by dx at I can be written as t of I plus 1 minus t of I minus 1 divided by 2 delta xi, but the beauty now is the order of accuracy is delta xi squared. So if you are evaluating the first derivative at xi, you are taking a node ahead I plus 1 minus I minus 1 divided by 2 delta xi, but you get second order accurate. So if you use the central difference, only thing is the value of the node at that, the value of the variable at that node is not considered. If you want to get dt by dx at t of I, but t of I is not used in the expression, okay, no problem, okay. So that is the, therefore this is the central difference this is the central difference approximation for first derivative. It is clearly seen that it is second order accurate because it is delta x square, okay. So this is the second order accurate. If you add, what happens? Shall we do that? if you adding 7 and 8, adding 7 and 8 we have T of is equal to dt by dx is gone, okay, and then 2 into then plus now we get an expression for d square t by dx square. Therefore, I think we need a number. Did I put a number? 9. I will call this 10. We will call this 11. Okay. Therefore, is equal to divided by two by delta x square. 2 is it's 2 gets cancelled, huh? No, then there is a problem. Is it correct? Yeah. No. No. There is a 2 here. Okay. What I have done is txi plus 1 plus txi minus 1 is there. Okay. Minus 2x. So the 2 remains in the d square t by dx square. Okay. 2 factorial 2 factorial get cancelled. This will be 24. So this will be delta x squared plus the square and square gets cancelled. It is still second order accurate. Okay, this is central difference, not forward difference. This is called the central difference. Okay, I plus 1, I minus 1, everything is there. What is the forward here? You got forward and backward. It's for an elliptic equation, right? It's for elliptic. So this is basically second order accurate. So now we got an expression for d square t by dx squared. It is called central difference. This can also be alternative derivation. Ij I plus 1j I minus 1j. So I can take an intermediate node I plus half j, I can take here I minus half j, okay. So I can get so dt by dx at I plus half j is equal to t of I plus 1 j minus t of I j divided by delta x. I can get dt by dx at I minus half j, that is t at I j minus t of I minus 1 j. So this is okay. Now I will say d square t by dx squared here is dt by dx at I plus 1 I plus half minus dt by dx at I minus half divided by delta x, okay. There is already a delta x here, delta x and delta x will give you delta x squared, and you will again get t of I plus 1 j minus t of I minus 1 j, t of I plus 1 j plus t of I minus 1 j, yeah, you substitute there, so you will get the same thing. But when you do this way it is very difficult, you can order of accuracy and all that, it is more involved to get it this way, but here it was straightforward. This is also another, so there are two ways of getting the same thing. Okay. Now we will go on to the, so we have got the finite difference representation of the first derivative and the second derivative. So therefore we can take up a simple partial differential equation and try to develop a finite difference scheme for getting the nodal value of a particular node, temperature at a particular node in terms of its neighboring nodes, that is the, so everything, all the goal of the finite difference approach is to replace all derivatives by algebraic equations. It is a linear combination of its neighbors. That linear combination stems from the fact that you can express everything in the form of a Taylor series. So the goal of the finite difference method is finally to use all the methods you have learnt in linear algebra to solve a system of equations. Therefore if you have to be good in finite difference and finite volume, you have to be good in linear algebra, how to invert matrix, whether it is worth inverting matrix more than 100 by 100, how to accelerate the convergence of a Gauss ideal, what is successive over relaxation, under relaxation, for steady, for unsteady what is the time step you have to use, cell Fourier number, grid Fourier number, unconditionally stable, conditionally stable, explicit method, implicit method, semi implicit and explicit, Crank-Nicholson method and so on. So you have to be good in all this, okay. Now this is the first, these are all the preliminaries. Mathematically how do you get the finite difference representation? We are heat transfer engineers, so our goal is to solve the heat transfer equation. So we will just take up the Laplace equation and see how we can use this to solve the Laplace equation. Is it clear up to this stage? T, yeah. Correct. Is that okay? Let us consider rectangular slab, same old. steady state 2-dimensional constant properties, no heat generation. So the governing equation is del square T equal to 0. No, T is not, okay. So what is the equation number here? So we will give a number for this, this one, half business. What is the equation number for this? 13, okay. So we will give a number 14 for this. So d square T by dx square plus now we write the finite difference expressions for both the d square T by dx square and d square T by dy square. For that what we will do is we will consider a node ij, we consider 4 neighbors I plus 1j and get the second derivative with respect to x and the second derivative with respect to y for t. Any problem? Okay. So I am keeping it as delta x can also change with the nodes, but let us start with uniform grids, okay. So number 16, okay. Now we can add d square t, let us say let delta x be equal to delta y, let delta x be equal to delta y, therefore d square t by dx squared means therefore therefore it is very simple. So the value of the temperature of the particular node is basically the arithmetic average of all the 4 nodes if which are equispaced from the node ij, okay. So this is the application of the finite difference method to the Laplace equation. So it will be slightly changed if you want to apply this to the Poisson equation where there will be a volumetric heat generation. Volumetric heat generation can take place in a medium if there is nuclear reaction or a chemical reaction which is taking place. For example, we want to incorporate heat generation, okay. Plus okay. Correct. If QV is equal to 0, it will reduce to equation 19, equation 22. So that QV delta x square by k will give an idea, of how much will be the contribution from the heat generation term. Okay. For example, if the heat generation, even if the heat generation is 1 into 10 to the power of 6, if generation 1 into 10 to the power of 6, suppose your delta x is just 1 millimeter, or then delta x will be 1 into 10 to the power of minus 3, delta x square will be 1 into 10 to the power of minus 6. So 1 into 10 to the power of 6 into 1 into 10 to the power of minus 6, if you have thermal conductivity of aluminum of 200, then it will not really matter, but if K it's bakelite or if it's cork, and then delta x is larger, then QV delta x squared by K will play its part in the algorithm. Okay. This can be reworked for a non-uniform grid space, non-uniform grid size where delta xi will be different from delta ya. So here you will, certain Ti's will get multiplied by delta y by delta x and all that. Okay. So this is essentially the formulation. So you can just keep on formulating for other steady state equivalents for the cylindrical as well as the spherical coordinates. In the next class, first 10 minutes we will just take 100-0-0 problem, apply it and see how we can solve it using the Gauss-Seidel method. We will just start with 3-4 iterations, and then I will tell the numerical scheme for a 1D unsteady conduction problem, and the rudiments of finite volume method also I will explain in the next class.